we were seeing it. And it would be nice to push this back to 10, 12 billion years. And that was the big question, whether Hubble could manage that. So every once in a while, good things do happen. And we happen to have a postdoc named Mark Dickinson at the Institute who is studying a distant galaxy, not because of its distance, but because it was a very strong X-ray source. And clearly something violent was going on. And at that time, which was just after the first servicing mission, which is just months after Hubble, the repair mission, had brought the telescope back to a useful performance, he submitted a proposal that required 32 orbits. That's 2 full days of the telescope time. This was much longer than anyone had ever succeeded in getting telescope time on the Hubble, which is a very sought-after instrument, as you can imagine. And we, every morning, had a tea where we'd get together and talk about science results. And I'll never forget the time in September of '94 when Mark came in, and I knew that he had this program but didn't know much about it. He came in and he showed this image of this galaxy that he was interested in studying. That is called 3C324. It's come from Cambridge Radio Catalog, which is what the C stands for, and that was object number 324. Here is a detail of this galaxy in a cluster of galaxies, and here you see something. What was astounding to us, it was one of the most exciting days of my scientific life. He had time at Keck telescope, which at that time was the only large telescope in the world, meaning 10 meters, and had gotten a spectrum of it, and from its velocity, Doppler shift, so-called redshift, was able to determine what its distance was. And recall, in that time, we were only able to look back 3 to 4 billion years in time. It was at a distance of 9 billion light years, more than double the distance of any galaxy that had been studied. And this was really mind-blowing. And this, so from its luminosity, we realized that this was a relatively massive galaxy. And here it is. So it was clear that Hubble at that time was able to look back in time much further than any other telescopes had been able to get us. Well, I had the good luck of being the director, and the contract that our institute has with NASA allows the director of the institute to schedule 10% of the telescope time. No questions asked, just part of the director's annual performance review. If I give it to my friends, out, you know. But if you get interesting science out of it, thumbs up. So at our coffee, and here's an image actually of Mark, who did it together with his colleague, Harry Ferguson, who had just gotten their degree, really young scientists. They didn't have permanent positions even at the Institute. We collectively made the decision, we've got to try to push Hubble to its limit to see how far back in time we can go. And so we addressed a bunch of questions here that I won't go into detail about. How best to do this. And what we ended up with was something that was very risky and somewhat controversial, but we thought was the right thing to do, and that was to take the telescope and rather than point it at some spot in the sky where we knew we'd get some result, to do just the opposite. We tried to look at an empty hole without stars in our own galaxies, to look back just to see what was out there in the universe that Hubble might be able to detect, realizing, and we determined that the maximum amount of time that would give us value added was 10 days, which was a huge amount of telescope time. It was much more than 10 times larger than any other program that had been undertaken. But I'm a risk taker, and so I said, let's do it. There were some prominent people who said it was a bad idea because this occurred right after the first servicing mission, We had, remember, the $2 billion telescope with a $1 billion servicing mission. Each one of the servicing missions cost $1 billion. So the public was wondering, well, was this worth it? We now spent $3 billion on this telescope. If a crazy director was going to take it for 10 days and take an image of a blank area of the sky and come up with nothing, that would have been very bad. But I thought it's something we had to do with that instrument. So what we did was to look at a region of the sky that had been studied before, that was essentially what you'd call a blank field. Now it's not quite blank. You can see here, this is a fairly large field of galaxies. So we knew that there was something there, but it was as good a hole, so to speak, in the universe as we could find. And we sat the telescope for 10 days, took exposures, a maximum of 45 minutes each, because detector noise starts coming up. And so we simply electronically added 10 days worth, and it turned out to be 345 separate images of the same area of the sky. We stacked them. We did it in several filters that basically gave us a colored image, and we call it the Hubble Deep Field. So this is what Hubble showed us with a large amount of observing time in an otherwise sort of blank area of sky. This galaxy here is this object here, okay? So some of these objects you can see had actually been seen before, but there are 3,000 objects here, only, excuse me, about 5 of which are stars. There's one, again, I'm not gonna, there's one. Apart from those 5 stars, all of these are galaxies. Some of them are relatively nearby. In fact, the closest galaxy here is one of these, 1 billion light years away. The most distant is that one, which is about 12 billion years look-back time. So the fact is, this is a core sample of the universe. The size of this image is a grain of sand held at arm's length, so a teeny part of the sky, but we considered it to be representative of what's out there. And so what we needed to do was to determine the distances to all these galaxies, so we could basically look at the structure of each of them in terms of their look-back time, and that would tell us how galaxies have evolved from their initial distant state to something that resembles more like the galaxies at the current epoch. In order to do that, we had to get their spectra to determine the redshift. Again, complicated, but there may be enough of you who understand this that you know about the Doppler effect, and the fact in the expanding universe, you take a spectrum, it shifts the wavelengths of the lines, and determine the amount of that shift, gives you the velocity, and since we know the rate of the expansion of the universe, you can determine its distance. So what we did with this image was to build up this image here, where we plotted the intrinsic brightness of those galaxies from, called luminosity, from the faintest to the brightest in terms of the look-back time. So here we are at the present time, 14 billion years after the Big Bang, which occurred down here at the bottom, and we could look back to within, thank you for dimming the lights, down here to 2 billion years after the Big Bang. And these are the images of those galaxies, those that were 2 billion years, seen as they were 2 billion years after the Big Bang, up to this one that is only 1 billion light years from the present time. So here you have the best observation of what galaxies looked like as they formed from this homogeneous gas up to the present time. So several things to note from this image. First of all these early galaxies tend to be smaller, and so these are all plotted, displayed at the same scale, same physical scale. These are smaller than these galaxies up here. These are bluer than these galaxies up here. And since color is an indication of the temperature of a star, when stars, groups of stars form, you tend to get these massive stars that are very hot and therefore bluish. And because they are luminous and they expend their stellar fuel very quickly, they die out. And then you're left with stars like our sun, which is not a relatively massive star, and it tends to be redder. So what is happening here is that these are blue objects because stars have just formed here at this time, and then those stars die out, and eventually you end up seeing only your fainter stars. And we call these galaxies red and dead. That is, most of the star formation has taken place, and all you're seeing now are these older stars like the sun that are slowly dying out. Secondly, hard for you to see, but take my word for it, that these tend to be fairly dysmorphic here. In fact, we call these train wrecks or garbage galaxies, no symmetry. And you start getting more symmetry and larger galaxies in time. Our conclusion, the galaxies from their gravity interact with each other and merge, and as they merge, because of a physical principle called conservation of angular momentum, all right, the spin is conserved. You start off with objects that are dysmorphic, but if several of them collide, that spinning motion